All right, ladies and gentlemen, today we're going to be going over Le Chatelier's principle. Le Chatelier was a French chemist who came up with a principle about equilibrium. So an equilibrium reaction in a closed system under stress will move in the direction to eliminate that stress. So what are the kinds of stress and how are they removed? So there's a few different types of stress that we're going to talk about today. So a shifting equilibrium point is going to relieve the stress. So instead of having our reactants go straight to products, in an equilibrium reaction, we have them in equilibrium. So we use this double-pointed arrow to show that it's shifting between reactants and products. The shifting point between products and reactants is going to relieve the stresses. So the kinds of stress that we can see in a reaction are changes in temperature. We have changes in concentration of either the reactants or the products. We can have changes in pressure, and we can have the use of a catalyst. So what is a catalyst? A catalyst is a substance that increases the rate of the reaction, but is not consumed by that reaction. So look at changes in temperature, our first stress that we talked about. In a type of reaction where energy is either released or absorbed, we can have either an endothermic reaction or an exothermic reaction, whether that's released or absorbed in the reaction. So an endothermic reaction is a reaction where energy is absorbed, and an exothermic is the opposite. It's a reaction where energy is released. So we have, if energy is increasing, it will shift away. It will shift the equilibrium point away from the energy. If energy decreases, it will shift toward the energy. So look at an example here. We have energy plus copper sulfate plus sodium hydroxide is in equilibrium with sodium sulfate and copper 2 hydroxide. So we see it's an endothermic reaction because the energy is going into our reaction. As temperature increases with energy as our reactant, we're going to shift the equilibrium point. K equilibrium shifts to the opposite side, so it's going to shift to our products. If we decrease the temperature, the equilibrium point is going to shift to the same side, so back to our reactants. In this case, with the temperature increase, we're going to shift to the products. So KEQ will increase. In this example, we have magnesium plus oxygen is in equilibrium with magnesium oxide and energy. It's an exothermic reaction because the energy is coming out of the reaction at the end. With the temperature decrease, we have energy as a product. So the equilibrium point will shift to the products in that case as well. All right, so concentration is the another kind of stress that we're going to see. It's going to act like energy, where we have in this example we have COCl2 in equilibrium with carbon monoxide and chlorine. So as we increase our concentration of our reactant, the equilibrium is going to shift toward products. And if we increase the concentration of our products, carbon monoxide, it's going to shift toward the reactants, so away from it. And if we're going to decrease the concentration of one of our products, okay, equilibrium is going to shift toward our products. All right, so next stress that we talked about is pressure. Pressure is only going to be accounted for when there's gases present. We're going to use Boyle's law in this. As our pressure increases, our volume is going to decrease. When our pressure decreases, our volume is going to increase. When our pressure increases, we're going to shift to the least number of moles in our equation. When we have our pressure decreasing, our volume increasing, we're going to shift toward the side with the most number of moles. So our example here, we have carbon monoxide gas plus oxygen gas is in equilibrium with carbon dioxide gas. We have to balance our equation first. So we have an odd number of oxygens over here, even number of oxygens over here. So we double what's making it odd. That's driving the reaction. Because we doubled the carbon monoxide, we have to double the carbon dioxide to balance our carbons. So now we have 4 oxygens on our reactants, 4 oxygens on our products, 2 carbons on both sides, balanced up. So take our coefficients and we count 2 plus 1 on our reactants is 3 moles of gas. On our products, we have just the coefficient of 2, so we have 2 moles of gas. So with an increase in pressure, we're going to shift toward the side with the least number of moles. So it's, yes, so it's going to shift toward the products. So it has 3 moles for our reactants, 2 moles for our products. It's going to shift towards our products. When pressure decreases, it's going to shift toward the reactants, the side with the most number of moles. Last stress that we're talking about is the presence of a catalyst. Remember, catalyst is speeding up the reaction, but it's not going to be consumed by the reaction. A catalyst is going to lower the energy of activation. So E sub A, what is E sub A? It's the amount of energy needed for the reaction to proceed. So it's for it to start somewhat spontaneously. So we have our energy and time diagram here, our reactants on the left, our products on the right. We have a change in energy there. In order to start, we need to get over this top hump on here. That's where we need to proceed the reaction. That, from our starting point to the top of that, is our energy of activation, our EA. Catalyst, when we add that in, is going to lower that curve, so our energy of activation is smaller. When we're using a catalyst, KEQ does not shift. There is no shift from that. It just speeds up the reaction. All right, we're going to find the KEQ shift for each of the following. We'll do that together in class. I will see you then. Take care.